This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you the new version of my DC power meter. So this version has a little bit of a correction because my previous PCB missed a few connections, but you can see that the layout is basically the same as the previous PCB's layout. All the parts and all the connections are at the same place. Here you can see even better that there is basically no difference between the two boards. There is only a small correction, which is just two pins connected together and to the ground via a wire. Since the board is unchanged, I could keep the old stencil, so I did not have to order a new, and the old stencil can be used. Here you can see the old board with the 0.96 inches OLED display, and if I remove the display you can see the rest of the circuit, and if you look closely you can see how I fixed the error in the previous board. I just soldered a small copper wire to the corresponding pins. So I prepared three different displays, a 1.3 inches and a 0.96 inches OLED display and an LCD display. This one is the 0.96 inches OLED, this is the 1.3 inches OLED display, and this is the LCD. So if we take a closer look on the circuit board, we can see two rows of pins for the displays, and you can see that the OLED display fits in the bottom one. You can see the order of the pins, VDD, GND, SCK and SDA, but if we take a look at the LCD, we can see that that fits to the top row, which starts with SDA. And as you can see, the outline of the display perfectly matches the board, because I actually designed the board or its dimensions after the dimensions of this display, so it perfectly overlaps. Before moving on, let me talk about the sponsor of this video, PCBWay. If you want to replicate my circuit, then follow the link in the description and you will end up on my project page where you can have my board, customize it, and then order it from PCBWay. And don't forget that PCBWay also has other services, for example 3D printing or CNC machining. So if you need some additional parts for your projects, then they can provide you with additional services. So please visit PCBWay's website and use their services for your next project. So here you can see the three different boards. The first one is the 0.96 inches OLED display board. All the components on the board are the same, so there is no big difference between the appearance except the display. And then this is the board with the larger OLED display. The display has the same resolution, 128 × 64, but it has larger pixels, and this is the 1.3 inches display. And then finally, this is the display that I originally wanted to use, but the PCB came much quicker than the LCDs. So then I built the board with the OLED displays first. And as you can see, the outline of the LCD matches the outline of the board, because as I said, I designed the board to match the size of the LCD. And you can see that it overlaps very nicely, and the LCD also looks great. So these are the power supply positive and negative pins, and then in series we connect together the 3 power meter modules, as you can see, and the final part is the Peltier cooler, which is the load. So the first unit is connected to the second in series, which goes to the third in series and to the Peltier cooler. By putting that red jumper there, I make sure that the circuits are powered by the actually measured rail, so they don't need an external power source. So let's turn on the power supply and see how they boot up and how they behave. And as you can see, they immediately powered up, they show the welcome screen, and then they slowly turn on and start the measurement. So after adjusting the brightness of my overhead lamp, we can see the displays better. So on the left side and in the middle we have OLED displays, and on the right side we have an LCD. And you can see that while the LCD is not switching pages, the OLED displays do. And the reason for that is just simply related to the screen size. So of course the LCD is large enough and it has large enough pixels that I can print everything on the same display, and I can still see the numbers with large enough characters. But both OLED displays have relatively small pixels and relatively small characters. So therefore I implemented the following strategy. First I show the voltage and the current, and then I wait for 4 or 5 seconds, and then I switch to the next page which shows the power, which is calculated from the current and the voltage, and I also show the temperature, which is the temperature of the power meter chip. So this temperature is basically the temperature of the silicon die, and since the power meter chip is relatively close to the shunt resistor and the traces which conduct the current which is being measured, it can also give us an indication if, for example, the traces or the shunt resistor itself gets hot. So that's a really nice indicator. And maybe another interesting fact to mention is that there is a voltage drop between each power meters. If we go from left to right, then between each modules we can see gradually smaller voltage and current values. And the simple reason for this is just we have different connections and a lot of cables between the power meter modules and the load. Therefore we experience some voltage drop, but that is normal with all these kind of weird connections. So this is what I wanted to show you as the upgrade for my project. So we should head over to my computer and I will explain you the code for the LCD, because I have already explained the OLED code. So let's go to my computer and check the codes. So now we are looking at the code, and before proceeding I just want to let you know a few things. So if you want to have the code for the OLED displays, that you can find explained in my previous video, because both of those OLED displays run on the same code and they are basically very similar to the code that I showed in the previous video. So please check that. And also, if you want to just get the code and you don't want to follow the video and copy the code as I explain it, you can support me on Patreon, and then if you are a supporter, then you can download the code and you can just directly get the Arduino source code file. And then the code that I explain here is the code for the LCD, and that is a bit different from the OLED display, but you will see that it is relatively simple. So let's start looking at the code. So we have two libraries here, and one is for the LCD. I found it on Google simply, and then the other is for the I2C communication. And then I just simply created an instance LCD here from the library. So this is what I will use to call different functions from the library. And then in contrast with the previous code, I moved out most of the variables from the functions. So we have a few things like the maximum current, power, bus voltage, temperature, current, and then an array of characters which will be used to be able to print floating point numbers on the display. So if you look at the setup function, when we power up the Arduino, we wait for 3 seconds. So we let everything to settle, especially the power meter chip. And then I just start up the I2C communication and then the display. And then as you could see, there is a welcome display when you turn on the power meter. So this is just the text. And then how the library works when we are talking about the cursor, then it is working by blocks and not by pixels. And if we move on the horizontal axis or x-axis, then each block is basically a block for a character. And then if we move on the y-axis, then each block is a line. So for example here, 5, that is the x, and that means that we start from the 6th block because we start the counting from 0. So 0, 1, 2, 3, 4, 5, and that is like 6 steps. And then 0 means 0, so that's the first line. And then we print this text in the first line. And then we move a bit down, so that is the 3rd line, so 0, 1, 2, that is 3 steps downwards. And then the indentation basically is a bit earlier than for the previous line, and we just print another text, and then so on and so on. And after printing, I just let the microcontroller hang for 3 seconds to have the display and have the chip settle more. And then I initialize the power meter chip. I will show these functions briefly, but they are quite carefully explained in a previous video. And then again we settle, and then we clear the display. If something is there from the previous let's say boot up or something like that, then the display will be cleared. And then since there will be only one page on the display, as you could see, there are no flipping pages or changing pages, then I can immediately print the static parts on the display. And that is just the text for the different units. So here there is no rocket science here. We just move the cursor somewhere where we want to have it, and then we print the corresponding text. And then we move to another line and we print another text, and so on. So we have voltage, current, power, and temperature. And then that's all. Here with this line, the setup function is finished. And then here we are inside the loop. So we query the sensor values. So we read the die temperature, and then the bus voltage, the current, and the power. And then once we get all these values, we move forward, and then we print the measured values. And here we have 2 functions, which is print first page and print second page. But in fact, we are not printing several pages. There is only one page, the main page or page number 1. But due to the implementation of the functions for the OLED, where I have 2 pages, as you could see, page number 1 shows the current and the voltage, and page number 2 shows the power and the temperature, then I had to use 2 functions there. And obviously I did not want to modify too much with the already existing function and structure, so I just kept these 2 things as they are in the previous code. But you will see that they are not complicated. But yeah, we print everything on the display, we wait 4 seconds, and then we restart again. So if you, for example, want a bit more vigorous sampling, then you just modify this number here, for example, to 1000. Then you get roughly samples every 2 seconds, because there is a delay between each query here as well. So that's that. And then again, I have explained these functions in the previous video, so please just refer to the previous video. But this is what we have here, so we can set the configuration with a certain command sent to the chip, to the power meter chip, and that is by just assembling some number using a binary code, basically a 16-bit binary number, and then we just send it to the corresponding register. And then the same as we want to configure the AD converter inside the power meter chip, we come up with some value based on the different bits for the different conversion parameters and measurement parameters, and then we write the corresponding register on the power meter chip, and then these settings are saved. And then the shunt calibration is the same. We have to provide the value of our shunt resistor. I have a 2 milliohm shunt resistor. Here is the exact type, and then we just have to calculate the LSB, and that is based on the maximum current that we are planning to use, and we have to provide that for the formula here. And then based on the formula which is provided in the datasheet of this chip, the INA 238 chip, we just calculate the calibration parameter, and here it happens to be exactly 1000. So that's a lucky coincidence that we have a nice round number. And once we calculated that parameter, we just send it to the corresponding register on the power meter chip. And then the coming functions are the reading functions. So if we want to get the shunt voltage, so that is the voltage drop across the shunt resistor, then we read a certain register from the power meter chip, and then we do some math on it, and then it's done. Then we store it in this variable. And then if we want to get the bus voltage, which is the voltage supplied to the load, then again we read another register, we multiply it with a certain number based on the settings, and then we get the bus voltage. Temperature, again, we just have a reading, and we have to throw away 4 bits. That is also stated in the datasheet, and that is thrown away by shifting it out to the right. And then that value is multiplied by 0.125, and we get the temperature in degrees Celsius units. Current, again, reading a register, and then multiplying with a factor here, and that's that. And then the power is also just reading a register on the power meter chip, and then multiplying that value by some factors according to the datasheet information. So then I implemented some functions to read and write the registers, and writing the register is quite simple. So we have this write register function which accepts 3 inputs in the argument. One is the address of the register, another is the address of the device. If we have, for example, multiple I2C devices which are power meters, then we can directly address them, and then the data that we want to use and write. So we just start the I2C communication towards our device, and then we write to the certain address that we want to reach. That is the register address. And then we write the MSB first, so the original 16-bit data shifted by 8. So that's basically the top part of it. And then we write the config data, which is the LSB. And then that's that. We wait for 10 microseconds, which is just enough delay for syncing the data with the power meter chip. And then for read response, we have this _2, because sometimes we can read 2 bytes, but some results are actually 3 bytes. So then I implemented 2 functions, but it's very simple. We reach the device address, and then we write to a certain register that we want to reach or read from. So then we request from the recently contacted device, and we request 2 bytes. And then what we do here is that we read the first byte into this 16-bit integer, and then we shift those bytes up, so they will be in the, let's say, MSB place. And then the rest is read from the power meter chip, and then it's combined together with the previously read and shifted response. So then that will be the full 16-bit response. And then the function just returns this number. And then the read response _3 does the same, but 1 extra time as compared to the previous function. So reaching the device, reaching the register, and then requesting 3 bytes from the chip. And then what we do there is that we have an unsigned long, which is actually a 32-bit variable, but we just care about the 24 bits of this. So first we read, and then we shift it up by 8 bits, and then we read again. So now we have 16 bits because it's combined with the previously read 8 bits. And then we shift up this whole 16 bits. So starting from 24-bit down to 8 bits, that is occupied. So from 8 to 0 bits, that is free. So then we read the next and last bit of byte, so the last part, to say it like that, and combine it with the already shifted and combined set of numbers. So then we will have the 24 bits altogether, and then we return with that 24-bit value. And then we arrive to this print first page function. As I said, there are no multiple pages, but this is how the previous version of the code was implemented, so I kept this kind of strategy of printing the information. And then in this function we deal with voltage and current. So I have some variables. One is the voltage itself formatted, and then the voltage unit. So then we know that the voltage returned from the chip, from the power meter chip, in millivolts. So then I decided that if the bus voltage is below 1000, so below 1000 millivolts, we want to keep the milliwatt unit. So we keep the voltage value unchanged, and we let then we let the code know that the voltage unit is millivolts. Otherwise, we are above 1000 millivolts, so we can print in volts. So instead of printing the millivolts, we do a division by 1000. So then the 1100 millivolts, for example, becomes 1.1 volts. And then we let the code know that we are using volts. And then here I just use this D2strf function as usual. So what we do is that we have the formatted voltage in floating point variable, or in floating point type, and then we want to store that floating point on a character array with a size of 7, and we want 3 decimal point, and we want to put the conversion value from float to character array into this print array character array. So then first I set the cursor for the unit to the corresponding place, and you can see that on the x-axis we are in the 8th block, and this will be next to the text voltage in the first line, and you can see that we are in the first line because the second number, which is the y-axis, is 0, so that's the first line. So then if the voltage unit was M, then we print millivolts. So then the first line will look something like this. But if the voltage unit is V, then the first line will look something like this. So then we will know that the unit is displayed in millivolts or volts, because we can see 1.1 in two cases. We measure 1.1 millivolt as the bus voltage, or we measure 1.1 volts as the bus voltage. So then printing the unit helps us a lot. And then we move to the second line, and that is under the text voltage, which is printed on the first line or in the first line. And then we just simply print the number, which is stored in the print array. And then I clean the array just to be sure that when I want to write in it again, I won't have any garbage in it. And then the current is really similar, except that we have 3 units, because we not only have amps and milliamps, but we also can have microamps. So then we have just 3 conditions. So if the value that we have is below 0.001, then we are in microamps, and then the current has to be multiplied by 1 million, so we can show it in microamps properly. And then we let the code know that we are using microamps. If the current is between 1 amp and 0.01 amp or 1 milliamp, then we format the current to show it in milliamperes unit, and then we let the code know that that's the unit. And then if we are here, so we have amps simply, then we keep it in amps, so we don't really change the variable here. We don't multiply or divide it, and then we let the code know that we have amps. And then we do the same conversion, so the current is converted into an array of characters like this. And then we move the cursor to the third line, again after the text current. And then we print the corresponding unit based on the selected unit. So here we will see this. And then if we have milliamps, then this will look like this. And finally, of course, it will look like this. And then we move to the fourth line under the text, one of these texts which are printed on the display, and we print the content of the array, which is the measurement value. And then we just erase the array. Then we print the second page, but once again, it's not the second page, it's just the second set of variables in this case. So now we focus on the power, and again we have 3 units, so similar to the previous implementation with the current, we have microwatts, and then we have to multiply it by 1 million and let the code know that we are in the micro units. Or if we are between 1 watt and 1 milliwatt, then we just multiply by 1000 and let the code know that we are in the millis region. And finally, if we have none of these conditions fulfilled, that means that the power is in the range of several watts, then we leave the power as it is, and then we let the code know that, yeah, that is in watts. And again, we do a conversion, move to the corresponding place on the display, and then that line based on the selected unit will look something like this. Milliwatts will obviously look something like this, and then the watts will look something like this. And then we move into the 6th line, so that is here, and we simply print the contents of the print array and then erase the array. And then finally, the temperature is very simple. There is no milli Celsius degrees or micro Celsius degrees. So then we don't need to do anything with the conversion. We simply just directly convert the floating point number to a character array, move to the 8th line, that is here, and then we print the content of the print array in that 8th line. And then we just erase the contents of the array so we can print in it again. And then that's that. This is the whole code. This is just 358 lines, so it was not a super long code, and hopefully not a super long explanation either. And once again, if you don't want to listen to this explanation, but you just want to get the code, please consider supporting me on Patreon. I uploaded the code there, and you can just get the Arduino source code file and directly upload it to your ATtiny85 microcontroller, and then you can use it as I use it in this video demonstration. So once again, don't forget to visit my website, because I put a lot of useful information there. Also check the previous video, because there might be some other information there which you could find useful. And also please check out PCBWay's website and check the link in the description, because then, for example, if you want to recreate my project and you want to build your own DC power meter based on my design, then you can just go to my project page, and then you can have the board manufactured by PCBWay, and then you can have it and use it for your projects. So I hope you liked this video, I hope you learned something, and see you in the next video.